So I'm at Loughborough University, and I've been researching additive manufacturing for probably 10 to 15 years, and close to the latter. And basically, I started my very first 3D printing with a custom print paths, just writing out XYZ values in Excel. It was for bioprinting. Later, then we moved towards like German 3D printing. I kind of kept this sort of distinct thinking, what can I do with custom print paths? And that's when I created FullControl. So I've given a few talks, and in this one I'm going to give a brief introduction to it. There's some software design philosophies that I've got, and then move on to how AI is hopefully just transform and sort of just work well. And let it that's the great spend. So the very, very brief bit about me, and then introduce what these custom toolpaths really are or came about. And then it's about focus on language models. I love and hate language models, and I think they generate a load of rubbish, and I use them all the time to generate a load of really good stuff. And there's really a balanced set of using them for what they're good at and not for what they're not. So what I really want, and why I haven't released this stuff yet, is because I want every single title that uses a language model to generate a toolpath that they will feel that is 100% successful. It might be too difficult to achieve or something, but it wasn't the language model's fault, and I'd hope that it was that didn't happen. Okay, cool. And that's all. So yeah, I started a mechanical engineering degree. That's it. I finished it as well, actually, in the end, and then moved on to a PhD at the same place. And that was studying mechanical properties of bioresorbent polymers, which we all now know PLA and use it a lot. I used it before it was cool and studying it at the atomic scale, and I was creating a stress analysis model of how atoms interacted. So got that nerdy side, but I also liked design and stuff. As I moved towards after my PhD doing research, that's when I was doing bioprinting and sub 2 every summer. Right. So we were using this polylactic acid for implants, fixed bones, so medical polymer, one of the very few regulatory approved ones. And then we were printing out grids, simple structures. We were growing cells on very cartilage tissue of nasal reconstruction, ear reconstruction, and that sort of thing. And then I moved to Loughborough, became a lecturer outside of the mechanical properties of the design side. And then AI came along. This is an image created by my daughters when they were 4 and 6 years old. And it was just incredible to get to that. We're just saying, I want a fairy, I want to have a little sister, and I want a little sister to have this kind of hair and stuff. It was great. Beautiful, beautiful image from their imagination. And I think the next generation are just going to think creativity and design in a different way, where it's your ideas that are important, your reaction to what you're creating and how you iterate your designs, rather than your technical capability to use Photoshop or to use other software, which historically was really a huge part of how good you were at creating CAD models. You can't create the best Formula 1 car model if you're not excellent at CAD. That's I think we're Jewish. So that's where I'm thinking what's going for this. And next, I'll come over here for a few of these. So custom toolpaths. Standard workflow, most of you know. We've got a 3D model, cut it into layers, reach out, identify the print path, then we print it, and then we do something with it. In research setting, we're often characterizing it and then trying to either understand or improve it. And then we come back. And often we're trying to print something with really intricate stuff, like little intricate pores or something. And we can see some pores got blocked, some of the surface wasn't as neat. And then we're really doing this backwards thing, like how do we actually, which bit should I pick? Should I put tiny little pores in my model? Should I change my slices, like sequencing of lines or stuff? And it's not a very nice way to think, like, how do I fix this defect? Because there's like 5 different things coming in that are all creating that one biggest defect. Next one. And that's why custom toolpaths are really nice. And I created this FullControl G-code design, and we kept it secret for a while. I was scared everybody was going to copy our research and stuff. And then I realized that it's more of a design philosophy. This is a useful tool that people can do toolpath design in Excel or in Python, but it's really the mindset of toolpath design which is different. So in this case, you create features like a line. I want a line on the print bed, and I want this wide, this high. and then I want to do a circle around it. And now if you just do that for loads of layers, you're going to have a split kind of cylinder, maybe you need a fluid mixing or something. You rotate every layer a little bit, and now you've got a twisted two-sided mixer or something if you want to take it. So you can build up nice geometry through very, very simple stuff. And this was supposed to allow people to do that without really understanding G code or having to go into maths and programming and stuff. Okay. And then what the beauty of that is if you're designing every single line and you see the end of one line has appeared on the surface of your model because it just overlaps the side literally. And none of the other 100 lines did. Then because you've designed every single line, you can just come straight back and iterate right at this point and say, okay, that single line, I'm going to make 0.1 millimeters shorter, and it's fixed. And it was a really tiny and obvious solution. Whereas with a slicing software, they're not expecting you to go and change the length of one line in 1,000 lines of infill. They don't want to give you that capability because everyone in the world has got to think, how long do I want every single one of my lines to be? And nobody wants to do that. That's just complicated. So that's the benefit of slicing. You can read complicated models, but you also can't do really intricate adjustments to every single little point because they are by definition not supposed to allow you to do that. They're making it easy for you. But every time you go through, you are losing the club design attention. So you're creating from a 3D model. You can't put in material requirements or surface tolerances in your CAD model. And you go into your CAD, but when it comes out as the STL file is all gone. And then you've got to sort of think, okay, how do I get those tolerances into my STL file or into my toolpath? And then it's a sort of line up, say, on the outside. So, whereas if you're designing with a couple of scratch, you can really go down these things. Okay, let's move. And this is the sort of parts you can get. So X, Y, and Z are all just now sort of free to design with. Normally X and Y is easy, and then you just do Z layers. Here it's just 3 numbers instead of 2. And this is showing a really cool part where it brings in a nice continuous path, and we can get like negative direction overhangs in the end, because the way of doing so conventionally impossible stuff. Then you can look at that's on. This type of structure very common in the kind of research field, things like catalysts, biotissue scaffolds, filters and things. Every line is part of the design, so it's not really worth creating a CAD model of the lines and then identifying where the lines should be. You just design the lines in the first place. That's what. Thank you. And then maths makes it super powerful. So designing those lines for this type of structure, now your mind's beginning to boggle out. How can I get all the X, Y, Z values of that? It's just going to be a nightmare. Just think of that. Whereas mathematical function for a spiral is simply this. X is that. It's just literally cos times by a number and that T number is just going from 0 to 1 or something. And Y is just that. Those plots show you what X and Y are doing, put them together in sync in 3D and you get this. And Z is just increasing constantly. So then you can kind of, that's so simple and it's getting quite a nice helix. If you start adding a few more terms into that equation, you can end up with really complicated things. So these are just the helix, and then I've also fluctuated X and Y a little bit more according to another way. And on the right, I've added a few more, and this is then a lampshade model where it's a single mathematical function where you can change all the parameters that go into it. And if you press right now, all of these that you see on screen now are just the same mathematical model with slightly different parameters. I'd say it's going to have 6 peaks instead of 3 peaks, changes the overall shape of that thing. And it prints beautifully, and then you can get people that don't want to do any maths, just to tweak a few parameters and get a really beautiful structure. Okay, next. This is a nice example. It's printing ceramics, and the quality that we got with this was just a step change from what it was a ceramics filament manufacturer that was sending these, and they just said none of them broke, and it's because even though it's full of weird dents and defects, they're all the same everywhere. So all of the defects are all shrinking during the sintering process in the same way, and it didn't lead to failure. And initially I was like, well, how can that? It's all so ugly, not ugly, but dented and stuff. But then we came to the conclusion it's just the fact that loads of problems all doing exactly the same thing aren't a big problem. Whereas if you have ceramics, they shrink a little bit here and a bit more here, that's when you get stresses that build up post spec. Okay, so those are a few of the examples. And then I've taken a few actual code examples to say how simple the actual maths can be. So next one. This is like a random mesh structure, something for like filtering, non-woven. So most of the materials you'll ever see around the place are generally non-woven. So ones you typically see that are woven in your clothes are actually kind of rarer and take things like toilet paper, like carpets and stuff. And this is an example of one of them. The design is literally, I'm importing a function that generates random numbers, and then I'm saying, for 1,000 points, give me a random point in X from 0 to 50, a random point in Y from 0 to 50, and then increase that a little bit. And it'll work. You might need to tweak parameters a bit, but it'll work. You'll get a random interesting mesh, and if you wanted to force it to be all on the edges, it would be a little tweak. And now you can generate a structure that will have some really interesting functions. And you couldn't do this in slicing software. You'd have to design every single line, the sequence of every single line as well. And it would just become it's just back and swing. This one then a bit more mathsy. We're saying for 10,000 points, increase the angle every time going around a circle, and then let's create this imaginary offset. If there was no offset, it would just do a helix all the way up 10,000 points. Because we've got to do that 200 points per layer, so then we've got to have so number of layers. Then the offset means that the X, the sort of radius is going in and out, the Z is going down and up, and you end up with this wavy thing. With that code at the top right, is that everything's like this sort of multi-axis, non-planar structure. And if you wanted to tie that maths to real geometry, it wouldn't be too hard to it. So, and this one less mathsy is just creating 4 points, like on a square, and then saying every time we go up a layer, we're going to repeat the points. We're just going to do some out and down, some in and up. And the amount they go out and down and in and up is just defined by this fraction of the layer height. So each layer is just coming in by half the layer height. And that's what we do. Next one. And then the other aspect is you can reuse designs. So here I've got a function that is to create a square wave, and I've got a function to move polar, which basically rotates a previous set of points. And then I've got a function to move, which is also triggered to copy it for a certain code. So I'm using the square wave function to say create this square wave. I'm using the polar rotator to say rotate it 180 degrees, and then I'm saying move all of them up multiple layers to get to. So now once you've generated that function once, you can reuse it across lots of different designs and build up complexity very, very sort of concisely. So now there's more code in the back end than those 3 lines you see there, but that code is not design specific. That's stuff you'd reuse again and again. Just like in CAD, you've got a polar array function, you've got a rectangle function. It's like building a microdam. Next one, and then this is a really nice example of something where you can go beyond normal lines. Think of this circle, that's got the same number of lines all around everywhere. The width is fluctuating, and what we do there is fluctuate speed as well, so we get constant volumetric flow rate, which is the only way to get maximum volumetric flow rate throughout our whole grid. And it's just there, that's quite complicated, the maths to actually do that for this sort of structure. Figuring out how wide the line should be at all these different points. But once you've done that maths once, you stick it in a function. I've called it convex paths. And now all you need to do as the designer or end user is say, here's my inner circle, here's my outer circle, fill it, do it for me, and I'll do all of that. I'll identify what your width should be of every line at every point, what your speed should be to get volumetric flow rate if you want that. And that's stuff that you can build. Anything you want, anything you could say, you can really do it. It's just a case of having someone with the skills to do it once, or someone else that's done it for you, or language models are going to really come and help us. And one, that's another same function as what I just showed. Doing a tensile testing strip where it's going to be really narrow, but it's really perfect quality. And people were printing this saying it's just getting ductility we've never seen before in any of our tensile tests, which makes sense because there aren't those defects that you normally get when you go from 2 lines to 1, which is unavoidable if you go from wider to narrow stuff. There is a RepRap function in some sites that will allow you to do a similar sort of thing, but it's not the same as designing the widths for every single line order. And then moving towards multi-axis. So now this is a multi-axis tube that we actually developed and printed the SMRRF 2.5 years ago. And again, we've got a few functions in the background, but that's the design. And these designs are everything. It's your CAD model, your STL file, your slicer settings. It's all there in one editable bit of code. So you can really come back and tweak things when it goes wrong or you want to improve it. Okay, so onto AI. Let's start with some opportunities, and then I'll go through some challenges and how I think we can actually make it really, really work. So the next one, I'll leave this for a minute. This was again about a year and a half ago or more now. I had a design in the VS Code, and then I was like going to create a new a star, just a star. Then I wanted to print multiple layers, and I was thinking, how good would it be to that? So I started typing, I'm going to create a function to create points for several layers of the star shape. And then I said, the user will choose a number of star tips that are in there. And then it took over and said, I think you're going to say this. And I was like, yeah, that's actually pretty good. That is what I was going to say. So I accepted that suggestion. Then I said, the function returns a list of all points for all layers. I started writing def, which means I'm defining a new function. And then it just did the whole function for me. And it's now figuring out and that's how to create a star shape in polar coordinates and doing a conversion from polar coordinates, which is like angular radius, to x and y. So it does that, and then I started saying, there's an extra step, I'm going to actually like to do this function, and here's all the parameters of it, so how many layers I want, and then as soon as I wrote it, I did the next bit, and then I started writing steps. This is from earlier in the design. I'd create a function and then say steps equals, and then run that function. And you can see that, so it did that. So it really was understanding everything, and it just worked first time. It's not a complicated kind of geometry to do, quite simple maths. But especially at that time, if you went and said, I want a toolpath for a star-shaped thing with multiple layers, to really touch a go as to whether you get a successful one. This had the benefit of seeing some of my earlier stuff, seeing what I meant by layers and things like this. But it was really nice that he just could do that. And then I was thinking, okay, I was initially skeptical 3 or 4 years ago about these models really being able to do something good. And this was probably the point where I thought, this is really useful for me now, actually, pretty cool. So same approach, I'm in VS Code, I've got a really nice model up, which is showing a few examples of things I've done, how I design and create FullControl code. And then I've come into the state-of-the-art language model code assistant on the right-hand side, so it can see my code, and I can talk to it, and it can go and edit the code. So it said, create me a toolpath for a bar, so it has 3 bulgy ribs sticking out the side. The ribs should get less pointy, spelled pointy like pointy, wider, but the same depth as you move up the bars. So less pointy, more sort of smooth. 2 of them should twist around the bars slightly so that they all start evenly spaced, like 12, 4, and 8, and they end up at 12, 3, and 6. Make the bars twice as tall as wide, and the ridge should stick out by about 10% of the bar's width. So that's enough information for many of you to just go and CAD that up. Okay, CADing that up is a bit of a weird one, but it's fairly clear. With language models, should be able to interpret what I want to get that sort of thing. I was using Claude Starnet 3.7, which was the best model at the time with GitHub Copilot. And it just gave me a proposed structure for my directory. If that was super annoying, I didn't want that at all. I didn't ask for that at all. It said create me a toolpath. It's just given me a proposed structure, no code in there at all. So I probably gave it a bit of a telling off and said actually create me or tried it again. Okay, there we go. I said, no, just look at the Python code. You can see now, base the design of the examples in there as a new section of code. Sometimes it would have done that anyway. Most of the time, it just got a bit confused that way. So then we got to this, and I was like, that's not bad. There's a few little gaps in the side, which are kind of confusing. They're quite pointy. The bulges coming out the side. And looking at what I asked for, I got 3 bulges. So at the right 12, 4, and 8 o'clock. It didn't end at the right position as I'd asked. And what else? The depths had actually changed as well as it was going, moving through. So it got quite a lot of things going on there. It wasn't a bad attempt. So we got 64%, and I was feeling still a bit angry about the first response, but at that point I was feeling maybe 20%. That it was going to be successful. They said there are gaps in the ribs, and they look kind of triangular at times. They go from smooth to pointy instead of the opposite. They don't match the pot position, but they're trying. Keep it 12, but rib at 12, and the bars should be twice as high. So it wasn't twice as high. Yeah, it was just still similar.
It's a demo, but I do this on the side.
Okay.
Tyler? Yeah, you're top now, so we'll get the rabbits.
Got you.
I thought it's going like till 11:05.
I had much money. Okay, I will blast through it, and then sorry about this. So then it was really didn't get those extra points very well. Got a couple, so I went again. No, you still haven't done them. Right again. It was getting a few more, getting closer to the one, and then I said make it twice as high. It just wasn't getting twice as high. It was the same bit as high. Tried again, and now it just got things completely wrong, and it reverted back. And that's what I'm feeling. So it was just real struggling to achieve the points. And if I took the code and put it in a really rubbish model and said, why is it twice as high why is it not twice as high? It just nailed it. So it was getting confused by its own, just too much information. So getting to like 10 minutes, getting 100% 6 steps, I think you just have to simplify it. So in this example, getting a young child to do a complicated-ish task is kind of never going to work. Asking them to do very little easy tasks will work much better. And then what I did was create that context in the background. And I created an instruction that said, listen language model, you're only allowed to return a sort of function that is for radius and angle. Don't do anything else. You're only allowed to return JavaScript. You're not allowed to do anything except these two things. No waffle, no explanation, just coding. So then I created the same exact instruction and got it almost perfect. One little tweak, saying 1 river 12 saying, got it perfect. This was using a model that was 2% of the cost of the one I was using previously. And that's just bonkers. It's the difference between these two cars. And it's, what are you going to do with this? If you're trying to compare these, like which one's faster, it's just bonkers. We're getting much, much better results. And we've taken our car, turned it into this, right? And that's only the beginning. Now I can say, right, that's the shape. I want to design the actual toolpath. Like they give me 60 waves, add an outer and inner one, make it so they all offset equally around the wall. A really intricate, detailed design, engineering designs. And then I can sort of see, okay, now I'm getting a twin walled structure looking great. You go right down to the tiny details of the end of one layer, how it moves around to finish the zigzag and connect to the next layer. And I could go into those details and just get it to knock it out. Thank you. So these are a few examples. If you want to see these, I'll put them on my stand, and then you can see this is the target I was trying to achieve, with some of them being geometry focused, some being like more toolpath focused, and got all of them. Really interesting geometries, all achieved with me using language like make it more bendy, more curvy, only at the bottom please. No mathematical language at all, as you see in all the prompts. And it's just making it so they're not overwhelmed. You need to select what important information they need, get them only to do the good stuff. So at our stand, if you come, we've got pill printer. These are the pill that we're printing, and it just started this morning. That's the first ones we've ever printed. It's going to evolve over the next 2 days. So please come and see us and see sort of what's changing with that. And that's related to a drug printing project where instead of sugar and sherbet, we're actually printing pharmaceutical tablets with closed. It's very
Fantastic. A round of applause for